Welcome. In this lecture, we will be taking the problems related to logarithm, which we have studied in lecture 2. But before proceeding further, I will give you the proof of two last properties which I have given so that you may understand it better. The properties given by me were a to the power of log a m is equal to m. This property I gave you last time. Now I am giving you the proof of this. Suppose our function given is a to the power x. This is an exponential function. Y is equal to. Now its inverse, for the finding out the inverse of this exponential function, what we have to do, we have to change the positions of x and y. So the exponential function of this, the inverse of this function will be less like this. Now we have to solve this equation to find the inverse of this equation number 1. As we have already studied that the inverse of this will be this function, and it is equivalent to y is equal to log ax. So y is equal to log ax is the inverse function of y is equal to e to the power x. Right? We have proved it here. How we came from here? We do a rougher as we did in the last lecture. X is equal to log a. It looks like this. Then we change the positions of x and y. Y is equal to log ax. So this is the equivalent of this y is equal to a to the power y. So a to the power x and log ax are inverse functions, right? Now we use a property of an inverse function. The property of inverse function is, suppose fx is a function, then as per the property of inverses, f inverse x is equal to x. Also f inverse of fx is equal to x. This we have seen in the lecture of inverse functions in the playlist which I have prepared for foundation mathematics. Now we take equation number 1. This is equation number 2. Our function were, what were our functions? A to the power x is equal to fx, and its inverse is log a, x to the base a. Now we have to find f of f inverse x. That is left hand side of equation 1. This will be f of f inverse x is log x to the base a. Now this is fx. We just replace log x to the base a in this equation, and we get this will be equal to a to the power, we just replace x by log ax. This will be this function, and we know this is equal to x as per definition of inverse function. So what we get? We get our proof that a to the power log m to the base a is equal to m. Now we have to give other proof. Please recall a to the power x and log x to the base a are inverse functions. Now we have to find f inverse of fx. This will be equal to f inverse of fx is a to the power x. Now we just put a to the power x in place of x here. This will be log a to the power x. As per the definition of inverse function, this is equal to x. So log a to the power x is equal to x. This gives the proof of our second property of logarithmic functions. So we have seen four properties of logarithmic function, that is log a to the base a is equal to 1, log 1 to the base a is equal to 0, and two more properties we have proved in this lecture are a to the power log m to the base a is equal to m, and log a to the power r to the base a is equal to r. These four properties we have already proved for logarithmic functions. Before defining other properties of logarithmic functions, we will take up examples based on what we have learned so far for logarithmic functions. The first question is, find the exponential equivalent of logarithmic functions. That is, it is given that log 216 is equal to 2 is equal to 4. Now we have to find the exponential equivalent of this equation. As we have explained in one of the lectures, to find the exponential equivalent, just write what is missing, to the power 16. Just write 2 to the power 16 and give it to 4 and change the position of 4 and 16. And this is the base, so the position of this base is unchanged. that is, our actual equation will become like this. So a exponential equivalent of this is 2 to the power 4 is equal to 16. Another problem, our logarithmic function is given like this. its exponential equivalent we have to find. What we do in the rough, we write 5 to the power 125 is equal to y, and we change positions of 125 and y. So our exponential equivalent will be 5 to the power y is equal to 125. This will be the exponential equivalent. Moving further, there are exponential functions given to us, and we want to write the logarithmic equivalent of this exponential function. So what we will do, we will take a rough work. Here it looks like 2 to the power 3. So in the log we will write log to the base 2 and 3 is equal to 8, and we will replace the positions of 3 and 8. What will be the logarithmic equivalent? Logarithmic equivalent will become like this. 3 is equal to log to the base 2 of 8. This will be the logarithmic equivalent of the exponential function defined here. These are very simple problems. I have just mentioned a method which I have devised to find the equivalent. Another question is, find the domain of these functions. Fx is equal to log x plus 4. Find domain. As we already know, for a function y is equal to log ax, the domain is that is what values x can take is x greater than 0. I have already explained from where this x greater than 0 had come. This had come from the exponential functions, uh, that the graph of the exponential function is already always greater than 0, and the log is inverse of a exponential function. So for log x plus 4, the equation will be x plus 4 greater than 0. This will be the domain, that is x greater than minus 4 will be the domain of log x plus 4. Similarly, we want to find out the domain of log 7 minus x. Now our domain should be something like this: 7 minus x greater than 0. On solving, seven minus x greater than 0 will become x less than 7. So our domain for this logarithmic function will be all numbers less than 7. So the domain will be minus infinity to 7, both open brackets. Right. Now I will take up the properties of logarithmic functions. There are 3 basic properties. 4 I have already told you. 3 more properties are there for logarithmic functions. What are those properties? Log to the base a mn is equal to log to the base a m plus log to the base a n, and log to the base a m upon n is equal to log to the base a m minus log to the base a n. When there is a division in the left hand side, then we get a minus sign. When there is a multiplication, we get a plus sign. And one more property, log to the base a m to the power r is equal to r log base a m. These are 4 properties we have already proved. This is the 5th property, this is the 6th property, this is the 7th property of logarithm. Now we will prove all these properties. Proof of 5. Right. Now we take let log a m is equal to capital A, that is we are dealing with the right hand side of equation 5, and log a to the a n is equal to b. The exponential equivalent of this will be a to the power a is equal to m, and exponential equivalent of this logarithmic will be a to the power b is equal to n. Right. Now what will left hand side will become? Log a, left hand side is log a mn. This will be, we just put values of mn from here. This will be log a to the power a dot a to the power b, and this will be equal to log to the base a, log to the base a to the power a plus b. This is since a to the power a into a to the power b is equal to a to the power a plus b. This is rule of exponent. Now we apply the property of the third rule which we have discussed, which we have proved also. the rule was a to the power log m to the base a is equal to m. Now we apply this rule in this equation. Here I am applying. What is the left hand side? Left hand side is log a mn, and right hand side becomes log a, you see, also one property is log a a to the power r is equal to r. We will applying this property, not this property. This property, from this property, the value of this equation comes out to be a plus b. So what was a plus b is equal to log am plus log n to the base a. So this proves our property which we have defined. Now proof of log m upon n is equal to log a to the base m minus log to the base n. I leave you just as an exercise, but I will take up the last proof, that is log a to the power r is equal to m to the power r is equal to r log a m. Again, for proving this property, we take let a is equal to log am. The equivalent of this will be a to the power a is equal to m. Now we already know the left hand side becomes log a m to the power r is equal to, we just put m is equal to a to the power a. This becomes log a m a to the power a to the power r. This will be log a to the power a r, right? Now we have already derived one property of logarithm, that is log a to the power r is equal to r. You see, this is a, this is also a, here it is a, here it is a, so this value will become ar, right? And what is a? A is log a m into r. We have just put this value here. So this proves our logarithmic property, that log a m to the power r is equal to r log a. This is a m. So we have proven 5, 6, 7 properties. Total 7 properties we have seen till now. There is another property of logarithm, that is if m is equal to n given, then log a log m to the base a is equal to log n to the base a. This is also called taking logarithmic of taking logarithm on both the sides. also if log a m to the base a is equal to log n to the base a, then this implies m is equal to n. These properties which we have defined, this is 5, 6, 7, 8 and 9. These properties will be highly used when we take up the exponential and logarithmic equations. These properties will be highly used. One more property is left, that is called change of base formula. I write just the formula and will give you the proof also. The formula is log m to the base a is equal to log m to the base b whole divided by log a to the base b. Here the base was a. Here in the numerator the base is b and denominator is the base b. M comes to the numerator and the base comes to the denominator. Now I will prove this formula. Let y is equal to log m to the base a. Its equivalent is a to the power y is equal to m. Now taking log on both sides, of this equation, it becomes log a to the power y is equal to log m. Suppose now base I have taken b, right? Now from the property of logarithm, the left hand side becomes like this, log b a, y comes here, and this is log mb, right? So what y becomes, y is equal to log bm divided by log a to the base b. And what was y? We have already defined y here. And this is equal to log m to the base a. So we have all proved our desired, this is m. That is from the base a, we have moved to base b in both the logarithms. This is how we can change the basis of any logarithmic function. So now I have finished with all the properties of logarithmic function. Now I just repeat all the properties so that you can remember it. First property is log a to the base a is equal to 1. Second property is log 1 to any base a is equal to 0. Third property is log a to the power log m to the base a is equal to m. And another property is log a to the power r is equal to r, and rest properties I have defined in this lecture. Log mn is equal to log m plus log n, any base you can take, and log m upon n is equal to log m minus log n. I'm not writing the base in any of the equations. And log a m to the power r is equal to r log to the base a m. And the last one was the change in base property. Log a m is equal to log m to the base b upon log a to the base b. So we have already written all the formulas and the properties of logarithmic functions. In the next lecture we will take some problems related to this logarithmic functions, and after completion of problems we will take up logarithmic and exponential equations. So by this we complete this lecture 3 of our series. Thank you very much for watching. Have a nice day.